Hello everyone and welcome back. Today we're going to continue our exploration of regression techniques and focus on two methods that are sometimes referred to as piecewise linear regression and spline regression. Let's just first go over the basic ideas of linear regression so that we at least have the fundamentals to build upon. So what we usually have in the simple linear regression case at least is one predictor x and one response variable y. And hopefully the data appears to have some linear relationship, maybe similar as so. Therefore, what we aim to do is to get some line that best fits this data, and hence we will have predicted values on this line that is going to be associated to beta hat 0 plus beta hat 1 x 1 per se. And for the simple linear regression case, we actually have formulas for these coefficients, beta hat 0 and beta hat 1. In particular, beta hat 1 is equal to the correlation between x and y times the standard deviation of y divided by the standard deviation of x. And beta hat 0 is equal to the average of our y values minus the slope of that linear regression line times the average of those x values. And one, of course, can show that the expected value of beta hat k is equal to beta hat k, or just beta k. In particular, these are unbiased estimators. Now, if we have the more general multiple linear regression model, which has the form y is equal to beta hat 0 plus beta hat 1 x1 plus beta hat 2 x2 all the way down to say beta hat p xp, where we have p predictors, and we of course can vectorize this in matrix form as just x times beta hat. Then if we use, for example, least squares regression for minimization for that particular beta functional, which we also typically do for simple linear regression, then we have the closed form representation of those coefficients. Beta hat is equal to xtx inverse times xty, where x is our design matrix for our multiple linear regression model. And that's perfectly fine. So what piecewise linear regression does is it breaks up our data into multiple pieces and fits a line on each of these sub pieces. Now, one can say, well, doesn't that really lead into the overfitting issue that multiple regression has? And in some sense, yes, but not always. So let's just go over some advantages that piecewise linear regression actually gives us that multiple linear regression does not. So let's first off start off by giving a data set. Let's work with one predictor just to keep things nice. Let's assume we have a data set that sort of looks like that, and then it sort of looks like this, and let's assume we have another part of our data set that sort of looks like that. And you may say, okay, well, obviously we have apparently 3 different levels for this particular predictor. So one can argue, okay, well, we have evidence to believe that there's confounding. Possibly other predictors need to be included in this model, and you wouldn't be wrong when you say that. So what we have here is, if you see this particular change in pattern over different levels of your predictors, then what we would probably do is partition our data set S, it could be bivariate or multivariate, it depends on your preferences, into multiple subcategories. So S1, S2, down to, say, for example, SK. For example, in this particular data set, this data would be S1, this data would be S2, this data would be S3, and what we would do is we would fit a linear data model for that piece, this piece, and that piece. And you could say, okay, well, that's great, but what does that sort of tell us? Well, on those subintervals, those lines will be more appropriate, but if we try to fit a linear model for the entire set of data, then you would probably get something like that, where our beta 1 hat is approximately equal to 0, meaning that that model is probably not that useful. So what are the assumptions that each of these sublinear subsets of our data set, what properties must they have? Well, the assumptions should be familiar to you. The fourth of them being independence in the observation. The first and most important is linearity. The second would be homoscedasticity, and the third being normality. So it's the same assumptions as linear regression or multiple linear regression, but now this must be true on our subsamples Sj, not necessarily S, right? Because we can see, well, the average of these for the means looks like that, the average of means looks like that, the average of means looks like that. So linearity assumption doesn't really meet on this particular case for the general set S, and also the variances on these sets might be completely different on each subinterval. But what we do is, well, if we have these four properties satisfied on multiple subintervals, then piecewise linear regression might be more appropriate than fitting a linear regression line on the entire set of data. Now that we know the basic ideas of what we plan to do, let's work through a particular numerical example. Let's assume that we have a set of bivariate data given by these sets above, where Sx is the x-coordinates, Sy is the y-coordinates, and these are ordered in the same exact rank as one another, i.e. 25 and 21 are linked together, 39 and 23 are linked together, all throughout to 65 and 32 being linked together. So you could fit a simple linear regression model on these two sets perfectly fine, but would that be appropriate? Usually you can start answering this question by looking at the scatter plot of the data. In particular, notice that the y values appear to be increasing as our x is increasing from left to right, but notice that once we hit 37, we have a sudden drop, and then it starts to relatively increase again. So if we look at our scatter plot, in some sense our graph looks like this. So would a simple linear regression model be appropriate for this data set? You probably would answer no. In that case, if you break this data set up and partition it into two or more data sets, would simple linear regression models be appropriate on those subsets? If you answered yes to that question, then piecewise linear regression might be for you. So let's assume we go that route and partition at this particular area. So what we plan to do is we want to take these first 6 points and these second 5 points and create simple linear regression models on those sets. So therefore we're going to create a simple linear regression model for this data set, and we're going to create another simple linear regression model for this data set. In this particular graph, those lines might be parallel, at least in terms of the graph, but it's not necessarily or even expected that they will be. One could go up, one could go down. You can sort of visualize that. For example, what if you have a data set that goes up and then suddenly goes down, where a parabolic model might seem appropriate? You can partition that at that particular corner point, and then simple linear regression that point, and then that point after that. So let's work out our example and see what we would have. So if we were to partition it with the first 6 and the last 5, then our first model is going to be of the following form. In particular, y hat is going to be approximately equal to negative 18.2 plus 1.09x, and our second model predicted values are going to be approximately equal to minus 30.6 plus 0.97x. These intercepts and these slope values are unrelated to each other because they're built with different sets of data. Now, we could build a simple linear regression model for the entire set of data, but as you probably imagine, we might get a slope close to or slightly near 0, right? Which would imply that that model would not be useful. So, one thing we should be also observing is that we cannot use values in the domain of the second model and throw them into the model of the first, because that wouldn't be appropriate. Therefore, when we're using piecewise linear regression models, in addition to our models, we also should be mandating or implying some domain for each of the models. So for example, the domain for model 1 should be based on the domain for our original values. Notice that we have a minimum value of 35, a maximum value of 31, and as we probably already know from regression, we should not go too far to the left or too far to the right of our simple linear regression model since our prediction values are based on those interior domains. Therefore, a reasonable domain you should be choosing would be equal to the minimum of that data set, which is 35, minus some margin of error, and then 51 plus some margin of error, the maximum of that data set plus some distance. And similarly speaking, M2 would be equal to the minimum of that data set minus the margin of error, and then 65 plus some margin of error. And it's not necessarily needed that these two intervals are mutually exclusive given some particular values epsilon 1 and epsilon 2. But generally speaking, how would you choose these epsilons? One easy rule is that these epsilons should be based on, for example, the range or variance of our domain values, right? So for example, if you have a lot of points covering a larger range, then you might be willing to make that epsilon a little large. But if you have a very narrow domain for that interval, then you probably will not be willing to go too far out from that narrow domain, right? Now, obviously that's how you would use this, and let's assume that we do not have any overlap. We'll discuss that a little bit later. But what do we gain from piecewise linear regression model? Obviously accuracy is a concern, right? So some good metrics that you probably should be considering, for example, if we do the SSE for the full regression model for our data, one can find that's going to be approximately equal to 258.93. Now remember, we only had 6 plus 5 equals 11 different numbers, right? And our y values are not necessarily large. So an SSE of 258.98 is usually a very bad sign. So if we do piecewise linear regression model and look at our partial SSEs, they better be a lot smaller. In particular, for our data set, one can find that SSE for our first model is approximately equal to 15.99, and the SSE for our second model is approximately equal to 3.15. Now, although the number of points in each of these data sets are substantially smaller, we are anticipating that these SSEs are smaller, but you should be able to show or see that proportionally they are a lot smaller than if we just factor in the sample sizes with respect to the SSE full. So definitely we do have a better fit for our data. But one thing that you need to keep in the back of the mind is the following principle. Piecewise regression, in particular piecewise linear regression, has a natural tendency to overfit data, especially if the number of pieces gets arbitrarily large. Here we have a number of pieces equal to 2 because we pretty much saw in our data set for our scatter plot that we had 2 clusters of data that are relatively linear. That's why we chose 2. But technically speaking, if you have a bunch of data points, for example, in this picture, what we can do is we can actually fit a bunch of lines between each of those points. So we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lines for 14 points. That's probably the most extreme you could ever do, and that would generate an SSE equal to 0. That's definitely what you don't want, so you better be choosing your piecewise linear subsets in a reasonable manner, and usually a scatter plot is the easiest way to go. And if you know any clustering methods, that will definitely help in this process. Now that we know the basics of piecewise linear regression, now let us increase the degree and introduce spline regression, which is often sometimes referred to as piecewise polynomial regression. So let's just go over the basics of polynomial regression in case you don't remember the basics of it. So as usual, to start, let us keep things basic and consider one predictor, one response. And let's assume that our data set has this following pattern. And let's assume that polynomial regression is a choice here. So one way you can approach this is with polynomial regression, right? So polynomial regression, because it doesn't appear to be linear, right? So if we use polynomial regression, we probably would fit a polynomial of degree 3 in this picture, because we have 1, 2, which is 3 minus 1, maximums and minimums. So degree 3, a degree 5, a degree 7, all of these would be appropriate in this particular case. Or we can do what we did in the last discussion and do 3 piecewise simple linear regression models. Simple linear regression models. Regression. So what would that look like? Well, we would probably break apart on these little pieces, do one line here, and another line there. And to some degree, they would provide similar but different results and SSEs, and also predictions as well. But nonetheless, polynomial regression is just one model, not 3 different ones. So it's a little bit more easier to work with because you don't have to consider domain partitions or anything like that. So let's just recall the basic analytics associated to simple polynomial regression. So for a predicted value for one predictor, so simple polynomial regression, usually our model is going to be of the form y hat is equal to beta hat 0 plus beta hat 1 x plus beta hat 2 x squared all the way down to beta hat p x to the power of p. And these are all the same exact predictor, say x1. So in case you don't remember how to sort of build this in R, or whatever language you're working with, our design matrix would be in the Vandermonde form. In particular, we would have 1s in the first column, x in the second column, x squared or pairwise squared, or our individual elements squared, all the way down to our individual elements to the power of p in the last column. And that would be your n by p plus 1 matrix for your design matrix. And then obviously our y hat will be equal to x times beta hat, where beta hat is equal to xtx inverse xty, because in some sense this is a multiple linear regression model, because that's just, for example, x1, x2, all the way down to xp in disguise. So that's how we would do simple polynomial regression, no piecewise, nothing fancy. And of course, we've discussed before multiple polynomial regression. So multiple polynomial regression. So for example, to keep things simple, let's assume we want to do a multiple polynomial regression model of degree 2, and let's assume that the number of predictors is equal to, let's say, 3, right? So our predictor model is going to be of the form beta hat 0 plus beta hat 1, x1, plus beta hat 1, 2, well, let's say 2, 1, x2, plus beta hat 3, 1, x3, and then plus beta hat 1, 2, x1 squared, plus beta hat 2, 2, x2 squared, plus beta hat 3, x3 squared, and that would be our degree 3. But notice that we're not having any interaction here. So we would probably have to have our interactions that add up to degree 2 as well. So for example, we would have gamma 1, 2, x1, x2, plus gamma 1, 3, x1, x3, plus gamma 2, 3, x2, x3, and that would cover your degree 2 metrics. Right, and you may ask, well, what about x1, x2, x3? Well, x1 times x2 times x3, that would be a degree 3 term, and we're assuming that this is a degree 2 model, so that would not be included, but you can always add that if you feel like all 3 are interacting with one another. So that's how you would do multiple polynomial regression and just simple polynomial regression on one predictor. Now let us go back to our previous example of where we would possibly want to partition our domain and do piecewise or spline polynomial regression on that particular data set. So let's consider the same exact data that we were working before when we were considering our piecewise linear regression model. So we're going to consider the same exact breakpoint for the same exact reason as before, because we saw that the data was sort of clustered in two independent pieces. So we're like, okay, let's partition this data set into these two regions, and let's fit some model on this data set, and let's fit another model on that data set. But instead of doing linear, let's do, for example, a higher order polynomial. In particular, let's assume that both of these are degree 3. Usually cubic polynomials are sufficient, provided that the length or the range of these intervals are not super large. So let's assume that we're going to have predicted values, let's say y hat j, and they're going to be of the form beta hat j0 plus beta hat j1, let's say x plus beta hat j2 x squared plus beta hat j3 x cubed, where j ranges from 1 to 2 because we have two subsets that we're partitioning over. Now, keep in mind when we're working with polynomial regression, we are introducing structural multi-collinearity into this particular model. So you probably want to standardize your predictors when building your regression model. Else you're going to have possibly a high condition number for that design matrix for your polynomial regression. So keep that in mind. So for each of these, let's standardize those predictors. And in case you don't remember, z is going to be defined as x minus x bar divided by the standard deviation of x. And then we're going to be squaring those z values and cubing those z values. And that's going to give you our new design matrix, but it's going to be in terms of z. So once we convert this into the standardized world, we're going to have y hat is equal to, say, zeta 0 plus zeta hat 1 z plus zeta hat 2 z squared plus zeta hat 3 z cubed. Right? So this would be our standardized model. And when you look at our data set, obviously our x values are going to be standardized around 0, of course, and this y value is going to be approximately equal to the average of our y values because we're not changing those. So if you look at our particular data set, what you're going to see is that, for example, these points is going to correspond to, for example, our subset 1, and the other set is sort of convoluted inside of that data set. So this is going to correspond to S2. Notice that they're sort of merged into their own little domains. But if we look at the pink and we look at the green, in some sense we see both linear trends. So if we were to sort of look at these in isolation, we can say, okay, we're going to fit a linear model on each of these anyway, which is pretty much what we're doing in the beginning, except looking at them in the same graph instead of separate. And when you standardize them, they sort of blend together because both of them are appropriately linear. Agree? So that's something to keep in the back of your mind, right? Because keep in mind, the pink is shifted with respect to the average of pink, and the green is shifted with respect to the average of green. Right. So once we have our standardized predictors, then we're going to have our predictor models. For example, y hat 1, if you work through this data, if you know how, is going to be 28.65 plus 8.72z plus 0.27z squared minus 1.47z cubed. And our second predictor is going to be equal to 27.83 plus 2.64z minus 0.95z squared plus 0.83z cubed. Keep in mind these are standardized coefficients, therefore they do not have any units, therefore you can compare them directly to one another. And you probably are curious, okay, well what about your SSE for that? So the SSE for the first subset is approximately 10.95, and the SSE is going to be 1.45 for that second model. And if you try to fit a cubic model on the entire set of data without partitioning it, you're going to have the model 29.94 minus 420z minus 137z squared plus 333z cubed. And you look at the coefficients and they're like, okay, well those are substantially different. But what's even more different is that this is going to be 151.27, which for the standardized world is very large. And one could say, okay, well, if I'm working with a degree 3 and I have a large SSE, one could say, can we overfit this data by sending the degree higher, right? Because notice that we're fitting two cubic polynomials and getting a total SSE of about 13 or 14, right? So even the total SSE is still substantially lower than the full SSE that you get when you try and fit for the whole one. So we're like, okay, well, what degree would a full model have to be in order to match the same prediction power that these two little cubic polynomials actually achieve? What I've done here is I've actually worked through these calculations for you to sort of give you some idea. So the degree 7 full will produce an SSE of 45.2, which is still substantially larger than those two. And if you do a degree 8, then you're going to have an SSE of approximately 8.76. So you would have to go all the way up to a degree 8 polynomial for the full model in order to achieve an SSE that is only smaller than one of the partial SSEs for your two cubic models. So let's sort of summarize that in the statements. So that means 2 degree 3s are better than 1 degree 8. And that is one beauty of piecewise linear regression and also spline or piecewise polynomial linear regression. The last thing that I want to mention in terms of piecewise linear and polynomial regression is how you're going to use these particular models. And I'm going to continue with the same exact data set to sort of guide this discussion. So if we look at our first model, and the domain that first model was built on, it was built on an interval 35 up to 51, and our second model was built on an interval of 55 to 65. Now, it's very easy to see that these intervals can overlap. For example, it's possible that I might want to fit a model for this data set, and I also might want to fit a model for that data set in green. We practically have a linear model there and a linear model there, where we've practically clustered those points together and clustered those points together, right? So the domain values obviously can overlap with one another, so that's not the issue, right? But if I were to use, for example, this particular domain input, which model should I be using? Should I be using this model or that model? That's where this piece gets a little bit more tricky to deal with. Let's briefly discuss the easy case where we don't have a substantial overlap between our domains. So one thing we can see, at least with our data set, is that we have practically a cubic model here, and we have a cubic model here. That is, we have a gap in between our domains. This is the easiest to fix. So one thing we can do is we can extend our model there and then extend this model outwards. For example, there, and now all values are covered, at least from the minimum up to the maximum value. So what we can do for a y hat 1 and our y hat 2 domain, because before our minimum value was 53 and our maximum value, what was it? I think 55, right? So those would be our two domain values. Oh no, it was 51 before, right? So 51 was the upper bound for the first domain and 55 was the lower bound for the second domain. So you're like, okay, well, what I can do is I can extend this or allow my predictions to go to the midpoint of these two values, and the average of 51 and 55 would of course be 53. So I can extend my domain, for example, it was 35 before and upper bound 65 before. And what I can do is I can do 53 there and 53 on the second, and whichever data set had the more values, I'll include it in that set. So let's do a bracket there and a parentheses there so we don't have any repetition, sort of like this picture I had up there where we have sort of two models that we may want to consider, and you possibly would even consider the average if you had repetition, right? And do notice that in this particular picture, these functions are not connected. That is pretty normal. Agreed? So also, in that particular case where you do have overlap, what would you do in that case, right? So let's assume that we have, for example, model 1 there, and we've clustered that together. And let's assume that we have model 2. Let's assume we've fitted a model there. Let's assume that they're designed on their appropriate domains, there and there. Obviously, if you're in this domain, you would only be using that pink domain. If you're on this particular domain, obviously you're only using that. But what happens when you have a domain input that's sort of on this intermittent interval? So obviously that point and that point would be your predicted values. So obviously you can use the one that you trust the most. You can take the average, you can take a weighted average, and that's probably what I would recommend, right? So the average probably would be that point there. But what you should do, this is just a recommendation. So the predicted value, let's call it y hat star, would be the average of those particular weighted values. So here, let's call that y hat 1, let's call that y hat 2, and what you can do is, for example, do n1 times y hat 1 plus n2 times y hat 2 divided by n1 plus n2. And that's going to pretty much give you a weighted average for your y hats. So it's going to be weighting the y hat that is built on the most data. And this actually is pretty useful provided that you're on the middle of this region. Obviously, when you're on the tails, it's going to be a little bit less misleading because most of the data is sort of clustered around the middle, i.e. the mean or the median. And also we're assuming that this data set should be approximately normally distributed, so we should not have as many values on those tails, i.e. it shouldn't be heavy tail. So those are just definitely some of the basic things they definitely should know about piecewise linear regression and spline regression. There's definitely different variations you could approach here, but those are the basics that you definitely should be familiar with and some of the ideas and strategies that is commonly used in the basic approach to piecewise linear and spline regression. There are more advanced methods that also mix in interpolation, where these curves have to pass through those points, but that is something a little bit more advanced that we'll get into at a later time. So I hope you enjoyed this video, and I'll see you in the next one. Take care.